Diffraction gratings. One of the most useful tools in the study of light and of subjects that emitted and absorbed light is the diffraction grating. This is a diffraction grating, somewhat like the double slit arrangement of the figure. This device has a much greater number n of slits, often called rollings, perhaps as many as several thousands per millimeter. An idealized grating consists of only 5 slits. It's 1, 2, 3, 4, 5 is presented in the figure. When a monochromatic light is sent through the slit, it forms a narrow interference fringes that can be analyzed to determine the wavelengths of the light. We first assume that the screen is far enough from the grating that the rays reach at a particular point P on the screen are approximately parallel when they leave the grating. Now, there's a parallel that leave the grating with angle theta. Okay, this is angle theta. This is angle theta. These are equal to angle theta. Okay, then the separation between the two rulings, delta x equal to d sine theta. D is their separation. Okay. Adjacent lines, they have paths different. Delta x, this one. Delta x equal to d sine theta. Then we apply to each pair of adjacent rulings the same reasoning we used for double slit interference. Satisfy d sine theta equal to m. Lambda is the maximum. M can be 0, 1, 2, 3, 4. M equal to 1 is the central maximum. Then have on both sides you have M equal to 1, 2, 3, 4. Symmetry. Let's look at 2. This is n equal to 2. Diffraction pattern. This is n equal to 5. Okay. Now they have different in numbers of rulings. When n increases, first, the fringes are sharper, narrower. You see this one? A sharper and narrower. Okay. Second, secondary maxima of low intensity appear. In this one, n equal to 5, you have a secondary maximum with low intensity. 3, the position theta maximum, okay, theta minimum are nothing to do with n. They are the same. You look at n2 and 5, the position are the same. Now we look at this one. This one was the intensity plus produced by a diffraction grating with a great many rulings, consists of narrowing peaks. Okay, here labeled with the order number of m. In the center we call m is 0. Okay, this is 1 symmetry on both sides. 2 and 3 is a narrow peaks. And you look at this, the picture of this diffraction picture. The corresponding bright fringes seen on the screen are called the lines, and they are also labeled with order number m. This is m equal to 0, m equal to 1, m equal to 2 on both sides. This is 0 first, second, the fourth without third. Okay. Order of the visible emission of light from hydrogen. Okay. Notice that the lines, the same lines, okay, to the center, are farther apart at greater angle, large M. Our gratings' ability to resolve separate lines of different wavelengths depends on the width of the lines. Okay. Now here we have half width angle. Okay. The half width angle delta theta half wave of the central line is here. Okay. Now we analyze this one like the double slit. The line with, okay, the position here is d sine theta. This is the first minimum. A sine theta equal to m lambda satisfy the minimum. The first minimum, this is the one. This is A. This is the width of the single representation. Here is ND. Okay. And so this one, delta theta, is equal to approximately equal to 1 lambda over ND. This is the central line. This is the first minimum, so this is called half width angle. This angle actually related to Rayleigh's criteria. If you have another second line, which the maximum must be outside the first minimum of this first one. Okay, so this angle actually is the minimum angle for the criteria. Okay, Rayleigh's criteria to distinguish two lines. In general, the width of the line's maximum is lambda over ND and cosine theta. We have more cosine theta. This theta is defined by the maximum condition. D sine theta equal to m lambda maximum. Because theta and this line had half width angle is delta theta. We don't prove it.
We'll use these sets of multiple slits on a slide to show the interference of light passing through the slits. This laser will be our light source. Here is the setup of laser, slits, and screen. This is the pattern obtained with a slit spacing of 80 slits per centimeter.
An application of diffraction gratings. We look at this is diffraction grating. We have a light shining so the slit and it go past this lens. Okay, and this is point is on this focus lens. So after this lens, the all light are parallel. It's shining on the diffraction grating. So the light will be deflected and we collect it at this angle theta. So when you satisfy d sine theta and lambda, we get a maximum line. This angle you can rotate. And this one, you see, from lambda, the wavelength of light, and theta, we measured, we can define the d, the separation of the grating. Okay? Or from d and theta, we can find the wavelengths. This is a picture of gratifying of cadmium. It has line 1, 2, 3, 4. Okay. As long as you have a combination of this line, then you can prove you have cadmium inside. Gratings, dispersion, and resolving power. Dispersion, to be useful in distinguished wavelengths that are close to each other, as in the grating spectroscope. A grating must spread apart the diffracting lines associated with the various wavelengths. So we give that definition. D is delta theta over delta lambda. This is this difference between the wavelengths of two lines. This is the angle they spread out. This one is larger, is better, right? Now look at this, how we calculate this one. we have this equation, d sine theta equals m lambda. This is the maximum. Okay, so we do the derivative with both sides. We get a d sine cosine d theta m d lambda. Okay, and this was delta theta delta d theta d lambda. So we found this one d theta d lambda equal to m divided by d cosine theta. Okay, yeah. So d, we look at the log. To achieve high dispersion d, we must use a grating of small grating spacing d. The smaller this one, the larger this one. Okay, and work in high order as large m. You notice that when you don't see the end, the number of rollings of this grating. Note that the dispersion does not depend on the number of rollings. The metric system for d is this angle per meter, or radius per meter. Resolving power. To distinguish lines whose wavelengths are close together, the line width should also be as narrow as possible. So we just have defined the resolving power at lambda average over delta lambda. Here, lambda R is the mean wavelength of two emission lines that can barely be recognized as separate. And the delta lambda is the wavelength difference between them. We look at carefully. This definition, right? We do it. We know this is the maximum. You have to see the line, the d sine theta and lambda. Okay, and we do the derivative on both sides. We get d cosine theta d theta equal to m d lambda. This is a difference, angle difference d theta for two lines with different wavelengths. And when we look at the width of this line, each line at this maximum at the half width is lambda over n d cosine theta. We have learned before. Okay. And this is actually related to Rayleigh's criteria. If two lines, they can be distinguished, the angle between them must be larger than this angle, the half-width angle. Okay, so with this one equal to this one in order to separate these two lines. And we put this one inside, we get the d cosine theta lambda or n d cosine theta equal to m lambda. And in this way, there's a d cosine theta in denominator, d cosine theta in numerator, it cancels out. So we find r equal to lambda over d delta lambda equal to nm. Wow, that's a nice number. You see that? To achieve the high resolution power, we must use the many rollings. The huge larger, the r is larger. Okay? Yeah. Let's look at in the detail. Definition is dispersion. Okay? And the resolving power. Okay. We look at two lines. They have the same delta L. One is one frequency, one wavelength, another wavelength. There's another wavelength. We look at this situation. You see the separation? For the same delta lambda, this one separate bigger. So this case, this grating, it has larger d dispersion, separate. And this one, we calculate is as large resolving power. Okay? One power. They narrow like a sling. Okay, so you look at this T, let's remember, I pick up especially, even though they separate larger, but you cannot distinguish them. Why? Because you see, this maximum is within the first minimum of the second one. So based on Rayleigh's discrete, you cannot distinguish them. But this one, even the D is smaller, the septum is smaller, but they are slim. And this one is outside the first minimum of the second one. So you can tell these two lines. So that's why dispersion and resolving power are different things. Okay? The resolving power of a grating must not be confused with its dispersion. Okay, we look at 3 grating. This is grating A has number N 10,000 and D separation 2,540 nanometer. So this nanometer is 10 to the minus 9 plus the thousands. Probably this is about 2 or 3 times 10 to the minus 6 meter. Yeah, and the first maximum is 13.4 degree. D. The second grating B have number 20,000, double. Okay, and D are the same as A. So the first maximum at the same angle, 13.4. This is D and up. Grating C is number 10,000 as A. So separation different. This is smaller. Okay. So the first maximum, the angle is different, 25.5 degree. Okay. This D and I. And we compare these 3, we find out. Okay. A and B, they have the same separation, so they have this is separation the same. So okay, so the D are the same. And grade A and C, okay, they have the same resolving power. They have the same resolving power. Why? Why? Because the number N is the same. And grade C has a high dispersion, okay? Because why? Because the C has the smaller d, so it's high dispersion, okay? And grating B has a high resolution. This is high because it has its larger number N. We look at the picture. This A and B, they have the same dispersion, this angle the same. And the C has the largest dispersion. And grating B is slim, as it has high resolution power.
We'll shine white light through these 3 diffraction gratings, each with a different spacing of ridges on its surface and onto a screen. This is the pattern from a grating with 3,000 lines per centimeter. Notice the first and second order spectra. Here is the pattern from a grating with 4,000 lines per centimeter. The spectra have moved farther out to the sides. Here is the pattern from a grating with 6,000 lines per centimeter. Now the spectra have spread out so far that only the first order spectra is visible. The colors are now much more intense than before.
Sample. A diffraction grating has 1.26 times 10 to the 4th rulings, uniformly spaced over with air 25.4 millimeter, 1 inch. It is illuminated at normal incidence by yellow light from a sodium vapor lamp. This light contains 2 closely spaced emission lines, known as the sodium doublet, of wavelengths 589.00 nanometer and 589.59 nanometer, only 0.959 millimeter difference. 8. At what angle does the first order maximum occur on either side of the center of the diffraction pattern? For the wavelengths of 585.00 nanometer. So we see the separation is L over N. L is 24.4 10 to the minus 3 meter. And this is 1.286 times 10 to the 4. So we get a D. is probably 2 times 10 to the minus 6 meter. Okay, all right. Okay, and we put the equation, the theta, the position of the m. Now we take m equal to 1, it's given. Okay, lambda d, we put the number inside, we get a theta. The theta is about 17 degrees. Remember, this you have to take the unit meter. This take the meter too. Okay, all right. Question B: using the dispersion of the grating, calculating the angular separation between the two lines in the first order. The D, we know this one. Okay, this definition of dispersion. Okay, and we know that when this calculate is m over d cosine theta. We find the theta. We have d. We have m. It's 1. Okay, the first order. Okay, so we get the d. You put them inside, we get the d. This is unit is nanometer. Okay, so this is nanometer. This is per nanometer. Remember, not meter. Once we know d, we know delta lambda, we know delta theta. So delta theta equal to d delta lambda. We put this number inside. Okay, we get an angle difference. Okay, very, very tiny. Okay, 3.606 times 10 to the minus 4 radians. Question C: what is the least number of rollings a grating can have and still be able to resolve the sodium doublet in the first order? This is the one we have to use it because R could n number. Okay, we know the average wavelength, we know the wavelength difference, we know this is the first order, so we can find n. N needed 999 rollings, about 1,000. Less than this one, you cannot distinguish these two lines. A monochromatic field of lambda 600 nanometer shines normally on the transmitting plane grating. The second maximum can be observed at an angle of 15 degrees with reference to the normal. What is the separation D of the grating? We know this is the second maximum, so satisfy the D sine theta equal to second to lambda. Theta is 15 degrees, lambda 600 nanometer, so you can find the D easily. Okay, we'll put a number inside. It's very straightforward. Okay. You have to use the meter as a unit. Okay, so we get D is 4.6 times 10 to the minus 6 meter. Question B: if a light with a wavelength difference delta lambda of 0.02 nanometer from lambda 600 nanometer can be resolved, then what is the least number of rollings in this grating? Well, then that means m equal to 2, the second order. Okay. Now we use this definition, resolving power. Okay. This is delta lambda 0.02, meaning lambda is 600 nanometer. Okay, and this should be equal to nm. M equal to 2, so we can find n. Okay, this n is 15,000